Welcome everyone to the webinar. I wanted to just set this up front for you that we have plenty of time for questions at the end. We ask that you stay on mute and put any questions you have in the chat, and we'll be sure to address them. Anything that we can't get to, we'll respond via email promptly. I would like to, and when we like your questions to be related to the presentation. If you have anything for us outside of that, email us separately, please. I'd like to introduce Dr. Bunce. Jim actually built his first photosynthesis system as a grad student 48 years ago, and performing leafy acid exchange measurements ever since. He's had 40 years of research experience with the USDA Agricultural Research Service in Beltsville, Maryland, as an environmental plant physiologist. His focus has been on photosynthesis, tomato-conductance, and plant-water relations and their response and acclimation in the context of plant adaptation to the environment. Most recently, adaptation to the global change factors of rising carbon dioxide concentration and temperature. I'm gonna let Jim take it from here. Please remember, keep yourselves on mute and put any questions you have in the chat, and we promise to address all of them. And let you take it away, Jim.
Okay, thank you. I'm gonna title my talk is Carboxylation Capacity Limits Photosynthesis at Elevated CO2 Throughout Diurnal Cycles. The Farquhar, von Kammer, and Berry photosynthesis model, which is the only game in town for the last 30 years. That model predicts that the stimulation and assimilation rate with elevated CO2 is larger when assimilation rate is limited by Vcmax, Rubisco carboxylation capacity, than when limited by J, which is electron transport. And that's true over a whole range of temperatures. This figure just shows assimilation rate as a function of temperature, and the assimilation rate is given here as a stimulation ratio of rates at 370 internal CO2 relative to those at 250 internal CO2. So essentially the change with a 1.5-fold increase in CO2 above ambient. And you can see the top marked with as Vcmax limited. The dark circles show that at 20 degrees, it's about a 1.35-fold increase in photosynthesis, and that factor increases as you go up in temperature. When electron transport is limited, indicated by the dark boxes, that stimulation is still there at all those temperatures, but it's considerably less when electron transport is limiting to photosynthesis. And the ratio between those two stimulations is about a factor of 1.2. So considerably more stimulation when photosynthesis is limited by Vcmax than when limited by electron transport. So here's the typical A versus CI curve, and showing the two different limitations: VC limitation in the solid black dots, and electron transport limitation shown by the open squares. And the actual assimilation rate at any CI is the minimum of those two. So it comes up fairly steeply and then flattens out as electron transport becomes limiting. So that's just a typical standard curve. The question is, what happens now when you lower PPFD? What happens to that curve or those curves? And traditionally, and almost all the current literature is assuming, without ever really testing it, it's just assumed that that only the J part of the curve, the electron transport part of the curve, is reduced when light intensity is reduced. So that's shown here as the open triangles now. The same curve as we saw before, but we've just added one more curve, which is assimilation when it's electron transport limited at a lower photosynthetic photon flux density. So that's the open triangles. So you can see that the stimulation and assimilation rate as you go up in CI just flattens out when at lower PPFD. So this is what modelers tend to assume, is that that's what happens in the real world. In the steady state, however, that is not what is experimentally found. And what we find is that the initial slope of the ACI curve is also reduced when you reduce PPFD. And this is just three, it's probably hard to read, but three examples of this, and there are lots more, that I published a few years ago. And it's just ACI curves at, for three different species at three different temperatures. And the multiple curves on each of those figure panels are just reductions in PPFD. So the top curve is highlight, then you go down in light with the open circles, and then you keep going down. And what you see in all those cases for three species at three different temperatures, in every case I've looked at, is that the initial slope of that ACI curve is also reduced when PPFD is reduced, which is not the way most people assume things work. So this is what happens in the steady state. And the outcome of that is, and it happens because Rubisco, it becomes deactivated as PPFD decreases. The activation state just decreases. And that's been observed by the biochemists for quite a while. What happens is that the relative stimulation of assimilation rate at elevated CO2 then is not less at low PPFD. And this is just an illustration of, again, an old publication of mine, looking on the y-axis is the ratio of assimilation rates at high to low CO2. And the x-axis is just the photosynthetic photon flux density. So you can see the top panel happens to be soybean measured at 4 different temperatures, and the bottom happens to be bean leaves measured at 4 different temperatures. And you can see as you go across in PPFD, there's no case there in either of those species at any temperature that the relative stimulation is reduced at low PPFD. And if anything, it's going the other way. But basically, they're essentially can't tell them from being flat. They're just flat curves. So the relative stimulation and assimilation rate is not reduced as you go down in PPFD. And again, this is for steady state leaves that have had time to adjust to the PPFD level that they're seeing. So the question for this seminar is, what happens in the real world? These are steady state. What happens in the dynamic situation? So we go to the field. Field environments, what actually limits assimilation rate at elevated CO2? Is it VC or is it J? So what I've done is a lot of in situ diurnal field photosynthesis measurements of paired leaves, measured one at ambient CO2 and one at elevated CO2, 400 parts per million or 600 parts per million. Done it now for 3 species, glycinemax, Labia, and Hammercallus. And those species were just chosen for having convenient leaf morphologies to do this with. No other reason. So for each of those species, we've done multiple diurnal full days of CO2 assimilation rates on days which are mixes of sun and clouds. And this is showing you leaf chambers from 2 different Cirrus 3s clamped onto 2 side leaflets of 1 leaf of a soybean plant, glycinemax. You can also see that the back end of each of those leaf chambers is shielded with a white foam board. And that's to prevent the ambient air temperature sensors from overheating in sunlight. So we'll talk about that in a minute. So anyway, so we take one of these leaf chambers is going to be run at 400 parts per million, one at 600 on essentially the same leaf, two side leaflets from the same leaf of a soybean plant. So that's what we're trying to do. We're trying to track ambient conditions. So we're tracking ambient air temperature. And as I mentioned, in order to do that with the CIRS-3, you need to shade the sensors that measure ambient air temperature to keep them from heating up in sunshine. You set the humidity, percent humidity on the CIRS-3. So you do this so that the water vapor inside the leaf chamber is approximately equal to outside. So whatever percent of incoming you need to do to get there, like 70% or 60%. And that depends a lot on your leaf material. So you just have to do that by trial and error. But you want to be matching ambient conditions. So you want the inside to be approximately equal to the outside. And that's only an approximate, is the best you can do on that. So one of these chambers is going to run at 400 parts per million, 24 hours, and one's going to run at 600 parts per million for 24 hours. And I'm actually sampling, taking data points every 5 minutes for each chamber. For light, we're using sunlight, and we need to be careful. Do we mount the chambers so that the windows are horizontal? And we want to prevent shading by other leaves at any time of day. So you have to be a little careful on the arrangement. So you get lots of data, measuring, sampling CO2 fluxes every 5 minutes, all day long. So out of those big data sets, what I did was select certain environmental conditions that I'm going to use for looking at how the photosynthesis is behaving relative to models of photosynthesis. So I've listed 3 of those here. One is midday, and I've actually compared before noon and afternoon, and I really don't see much difference in terms of how the plants behave. But so midday, stable, high PPFD, full sunlight. So sun here, PPFD greater than 1200. And stable, not changing with clouds, and not changing substantially with time over a 5-minute period. The second condition is early in the day or late in the day, stable, low PPFD levels with PPFDs less than 400. So, after dawn and before sunset, no clouds, nice, stable, where you get steady rates. And the third condition, which I'll talk about, is in the middle of the day, looking for events after a sudden decrease in light because of clouds. So I'm looking for periods where I get stable, decreased low PPFD in the midst of a sunny day. So I'm looking for conditions where the drop in PPFD is more than 800 because of the onset of clouds. So those are the 3 conditions I'm going to concentrate on looking at in terms of comparing the stimulation in photosynthesis between the leaves kept at 400 and those kept at 600 parts per million. So in terms of analyzing what the leaves are doing, the modeling of assimilation rate. For the first step is the leaf kept at 400 parts per million. Use the assimilation rate, the observed CI, and the temperature to calculate, use the model to calculate what VC is and what J would be from the Farquhar, von Kemmer, and Berry model under 2 assumptions. One is that VC is limiting, and the second case that J is maximum is limiting for that leaf at 400 at whatever CI and temperature it is. For the corresponding leaf at the same time at 600 parts per million, use the A value, the CI, and the temperature determine whether that assimilation rate measured at 600 is better predicted from the VC or from the J that you obtain from the 400 part per million leaf. So that's the analysis. So this is just an example of for soybean glycinemax, and just to show you that I'm looking at basically a sunny day where light PPFD goes up to close to 2000, but it's interrupted by brief periods of clouds in the middle of the day. Leaf temperature, this is a fairly warm Maryland day, so maximum temperature is around 37 or so. And in the 20s in the morning and the afternoon. And this is just 5-minute records of assimilation rate on the top panel and substomatal CO2, CI values recorded for those leaves at 400 and at 600 parts per million. And you can see from the top panel that you get sort of a normal diurnal curve of photosynthesis, with the elevated leaf having higher rates all through the day. And you see the interruptions by sunflex, by clouds in the middle of the day. And the CI values, you can see that the ambient one tracks very, very nicely flat in the middle of the day. And both of them are higher in the mornings and in the afternoons, but fairly, and the elevated one is actually tracking slightly upward all day long. At high light. And then you can see again, with the clouds going through, you get brief periods where the CIs jump up as the stomates don't have time to react to the sudden decrease in light. So assimilation rate crashes faster than the stomatal conductance. So you get these bumps in CI. So all those CI values are important for the data analysis. So doing this for several days for each of these 3 species, I'm going to sort of summarize what I get out of doing that. And we'll start with the soybean glycinemax. And this is taken from 3 days of doing these 24-hour CO2 responses. So the first column is the PPFD criterion. So high and constant, you see A, ambient. So that's the assimilation rate measured at 400 parts per million, and the assimilation rate measured at elevated concentration. Then the 4th column over is assimilation rate modeled, modeled for 600 parts for the elevated condition, assuming that it was limited by VCM. And again, you can see that at the high CO2, the actual assimilation rate at elevated CO2, that modeled based on assuming that VCM is limiting, is very close to what we actually observed. If you had modeled that assimilation rate is 600 parts per million based on electron transport being limited, it's shown in red there because it's an underestimate of the actual rate. So we see that at high constant light intensity, we are in fact better off modeling assimilation rate at elevated CO2 as being limited by VCmax. The surprising part, to some people at least, is at low constant PPFD, early morning, late afternoon, again, you get a stimulation in photosynthesis from 8.7 up to 14.1. And again, that is very well modeled by assuming that VCM is the limiting factor at elevated CO2. It's not well modeled by assuming that electron transport has become limiting. So that electron transport value of 12 underestimates the actual value. On the other hand, when you get a sudden decrease in PPFD because of clouds, the situation reverses. And here we still get a stimulation from ambient to elevated, but now we're better predicting that if we assume that we have become electron transport limited at elevated CO2, and we overestimate if we assume that we stay VC max limited. So for a normal diurnal pattern, when light is slowly changing, then no matter whether the light is high or low, we are limited at high CO2, or limited assimilation rate is limited by VC max, not by electron transport, even at low light. That changes when you get a drop because of clouds coming by. And this is a summary for 3 days for Hammercallus, and get exactly the same pattern. Again, we get this, these guys tend to operate at lower CIs. So you have a big stimulation from 400 to 600 parts per million. And that's very well predicted from the rate measured at ambient. If you assume that rate at 600 parts per million is still going to be limited by VCM. So 20.4 versus 20.6 is a really good prediction. If we had assumed that electron transport were limiting, then we would significantly underestimate assimilation rates at the high CO2. And the same is true again at low but constant stable PPFD. Again, we still get a stimulation in photosynthesis, and that stimulation is well predicted if you assume that VCM is limiting, but not well predicted if you assume electron transport is limiting. And again, just like soybean, when you get a sudden decrease in PPFD because of clouds coming by, the pattern flips. That now electron transport is limiting for a brief period of time, and VCM overestimates your rate. And looking now, moving on to the third species, which is Labia. Again, we get exactly the same pattern. The assimilation rates in the high constant PPFD are best modeled by assuming VC max is limiting, not surprising. But again, at low but constant early morning, late afternoon photosynthesis still is stimulated, not as much, relatively speaking. But again, that's better predicted by assuming that you're still VCM limited, not electron transport limited. And again, like the other two species, when you get a sudden decrease in light because of clouds going by, the situation flips, and you're better modeling that by assuming electron transport is limiting rather than VCM. So it's complicated. Depends on how fast the light is changing, whether the leaf has time to adjust when it's changing fairly slowly, in which case VC stays limiting the whole time, or when you get a sudden change in light, sudden decrease in light, then electron transport is limiting. So the conclusions from these is during cloudless periods, Rubisco activation status changed with PPFD level, and at ambient CO2, assimilation rate was always limited by VC, not by electron transport. And in these three species, at least, VC still limited assimilation rate at 1.5 times the ambient CO2. And that occurred even at low PPFD. And thirdly, after abrupt decreases in PPFD due to clouds, electron transport did become limiting to assimilation rate for up to 10 minutes in these species at both CO2 levels. So, further questions. One of the reasons I did this in the first place was sort of reacting to a paper in the Proceedings of the National Academy in 2014, which said that real global photosynthesis has increased with increased atmospheric CO2 more than ecosystem models predicted it should have. And to my mind, the problem with that was that the models have assumed limitation by electron transport at low ppfd and in shaded leaves. So that was what stimulated me to look at this in the first place. The question then, after looking at these three species, the question is carboxylation capacity limitation predominant even at low ppfd and or at all elevated CO2 levels? So what about other species? What about how low does ppfd have to be? What about higher or lower CO2 levels than I've looked at? There's just not a lot of literature out there and on this question of what is limiting to photosynthesis, whether it's VC or J under real field conditions. And what is out there, some of it is done with what I would call poor methodology, and they get some bad answers. But basically, there's just not a whole lot of data out there. There are other ways to get this information other than doing these kind of diurnal curves at ambient and elevated CO2. But the other ways of doing it are not very efficient, which is why that data is really rare. So being able to set up instruments to track gas exchange periodically all day long at high and low CO2 is just a more effective way to get this information, which again is kind of vital if we're going to understand what ecosystem CO2 exchange is going to look like as CO2 goes up. And with that, I'll open it up to any questions.
So thank you, Jim. That was terrific. First question that has come through, how to differentiate the carboxylation and light limitation with triosphosphate limitation while measuring?
Yeah, I didn't mention triasphasite limitation only because I never encountered it in these diurnal curves. And triasphosphate utilization happens occasionally. Mostly it happens when temperatures are lower than what the plants have acclimated to. And that wasn't ever the case in these diurnal curves. These are all done on fairly warm days. So I never, the symptom of triasphosphate utilization is premature CO2 saturation. So that your actual rates are lower than you would predict either from VC or J. So that the reason I didn't talk about it is just because it never happened in these experiments. It doesn't mean it never happens anywhere at any time, but it didn't happen here. So that's a TPU would be another complicating factor, but that's why I didn't talk about it.
Okay, moving along. Can we generalize the pattern of assimilation at high and low ppfd between both C3 and C4 species?
It's a good question. The problem with trying to do this with C4s is that the models are not quite there yet to give us unambiguous answers without simply from looking at diurnal ACI or diurnal patterns of photosynthesis. With C4s, it's really hard to know without a lot more ancillary measurements what the limitations really are. So I'm not really prepared to extrapolate to C4s.
Okay. And do you know what the reason that at low ppfd, the model is under-predicting the electron transport?
Well, the reason that VC stays limiting is just because we believe that the Rubisco activation status decreases when the leaf has been exposed to lower, less than saturating ppfd. So it's a change in the activation status of Rubisco with less than saturating light, and that's what keeps VC being limiting rather than electron transport. And that, the deactivation, Rubisco activation is controlled by another enzyme, the activase enzyme. And there are cases where that activase enzyme activity changes with things like light and changes in some cases with temperature. So there's a mechanism in there for why activation of Rubisco changes. So that's the explanation why VC becomes limiting at low light, is because Rubisco has become deactivated because of lack of activity of the activase enzyme.
Okay, great. Moving along. Is the relative humidity likely to largely impact carboxylation efficiency?
Yes and no. It's funny. Years ago, the initial assumption was that VPD affects metal conductance in most things, not everything, but most plants. VPD affects metal conductance, and often in the laboratory and often in a lot of species, even in the field, that's all it does, is it changes to metal conductance, which limits photosynthesis by changing the CI. But that's not always all it does. There are certainly lots of examples now in the literature where VPD seems to affect carboxylation capacity as well as to metal conductance. So, and that there are differences in species in how that happens. And part of it is in the field, when you get a change in VPD, you're also affecting probably the transpiration rate of the whole plant, which may dry the plant out and affect carboxylation capacity in that way as well. So there's no simple answer to that.
Okay. We'll do a last call for any questions. That looks like that's about it, Jim.
Okay.
So Carrie.
Yeah, thanks, Jim. As always, great presentation. If anyone thinks of questions after the fact, feel free to email me and I'll make sure those questions get answered for you. And we thank you for your time today, and sign up for webinar updates if you want to find out when the next one's coming on our website. And thank you for your time today. And again, thank you, Jim.
Okay, thank you.
To learn more about how the CIRUS-3 portable photosynthesis system can enhance your research experience, visit ppsystems.com.